Okay, welcome to the annual Rockwood Memorial Lecture of INC. So these lectures are in honor of Paul Rockwood, who was a UCSD alumnus, in fact a pioneer in machine translation 25 years ago, who here at UCSD made initial waves in this field, way before it now became popularized and it took off. Unfortunately, he died tragically in a mountaineering accident, but the legacy continues, lives on here, and we're delighted every year to honor with this event a luminous speaker in fields of neural computation, right? And we had people here like Jeff Hinton and luminaries in the field that come here every year, give a lecture. And today we're very delighted to have with us Pietro Perona from Caltech, and I'll let Terry do the introduction.
Well, it is a great pleasure to introduce Pietro, who is coming to us from Caltech. He joined the faculty there in 1991, which was just a short time after I moved here to La Jolla. So we're kind of, our careers have gone in parallel for the last 30 years. He hails from Padua, Italy, and received a degree in electrical engineering there at the University of Padua, and a Ph.D. From the University of California at Berkeley with Jitendra Malik, which was a very good start in computer vision. He is currently the Alan E. Puckett Professor of Electrical Engineering and Computation and Neural Systems at Caltech. The CNS program that he helped to found was the first program in this field, neurocomputation, computational neuroscience, and really forged the way for a whole generation of students who are out now, who have been trained and are on the faculty at many universities around the world. Our computational neuroscience training program followed about a few years later, but they were the pioneers. One of his real contributions to the field of computer vision was a data set called Caltech 101, which is not a course. It was a set of images which served as a benchmark for a generation of people who were trying to develop systems for categorizing, classifying images, categories of images. And so one can call him the father of Caltech 101. And since Fei-Fei Li was his graduate student, he's the grandfather of ImageNet, which played a very important role in the breakthrough that occurred about 5 years ago. This was the deep learning network that really transformed computer vision back in 2012. He's had many honors. In 1996, he was named the NSF Presidential Young Investigator Award, very prestigious. He's received an award for the Longwood-Higgin Prize in 2013 and the Kundrik Prize for Fundamental Contributions in Computer Vision in 2010. Now, one of the areas he's contributed, which is particularly important for those of you who are interested in neuroscience, is the fact that he's applied his tools and techniques in computer vision to trying to track animals like mice and flies in order to automate the acquisition of data about their behavior. And this is really having a transformative effect in neuroscience because we can now look with very high fidelity, both spatially and temporally, and see how species, for example, like flies, interact with each other and how the brain activity may give rise to that behavior. So he's made many important seminal contributions in computer vision. So it's a great pleasure for me to have him give us the Rockwood Lecture 2019.
Okay, so it's always fun to be in San Diego, and it's beautiful weather, beautiful place, and lots of interesting work going on. I spent a day touring different labs at fast speed and enjoying all the work that is going on. So as Terry said, we collected the Caltech 101 data set at the beginning of 2003, 2004. And the reason was that I had thought at the time that visual categorization would be an important problem in computer vision. And so most of you who are sitting here were barely babies at the time, or even maybe not even born, who knows. And so you wouldn't know that at the turn of the century, computer vision was all about geometry. So if you would go to a computer vision conference, 90% of the papers would be about geometry, theorems about how to reconstruct shape from lines, points, and this and that. And the people who were doing visual categorization were very few. There might be 2 or 3 papers about visual categorization, and they were all using 2 data sets, one of faces and one of automobiles. And they were saying that they were doing categorization. And so I thought, we are overfitting terribly these 2 data sets. We're not really discovering anything about categorization. We're discovering how to work systematically on cars and faces. And so let's collect images belonging to a number of categories. And so Fei and I talked about it for a while, and I told Fei, well, so Fei first collected maybe 4 or 5 categories. We had leopards, we had motorcycles, a few. And I said, oh, it's time to have more. And she said, okay, so get 10 categories. And I said, no, more than 10. And she said, well, how many? Maybe 15, 20? And I said, Fei. And so I thought, all of you are students, you have an advisor, you know that you get sometimes into slightly tense moments in which advisor wants a little bit too much. And so she was pulling back and I was pushing. And I said, 100, Fei, 100. Because I got slightly ticked off. And so she said, okay. So she went away. And 2 months later, she came back with 101 categories because she wanted to show me that she had not pulled back and been parsimonious. And so that was the first data set, and it became very popular. And within 2 or 3 years, the whole community in computer vision switched from geometry to categorization. That's not the whole, but 80%, or a large number. And then Fei kept going, and she built ImageNet, which is a much bigger endeavor, which had the effects that you know about, and I'll talk about that a little bit later. So in the process of collecting and annotating data sets, we started using the Amazon Mechanical Turk, and we realized that people have different ideas about what is there in a picture, and they may not even be terribly careful. And so we started thinking about how to harvest information from people, and we realized that what you're used to in machine learning, namely the paradigm in which your data is clean, you have X and Y, and you train and test, well, it's not true in the real world. Truly, in the real world, you have data, and the annotations are in the eye of the beholder, and you have to work hard to get them, and they're never too accurate. And so we started thinking about how to build a loop between a machine that has to trust the people to give it the right information. It has to be somewhat skeptical, and we realized that this is the right way to think about machine learning, at least in some environments. And so it started with a picture that my father-in-law sent me a few years back, and he knows that I like to pick mushrooms in the woods, and he said, well, can I eat this one? And this got me very worried because I sensed that this mushroom might be poisonous, and I love my father-in-law, and I didn't want him to get sick. And so he said, well, but don't admire it, but don't pick it up. But something that struck me was he's a very technophiliac guy. How come he wasn't able to use Wikipedia to classify the mushroom? He has his iPhone, he has the mushroom, everything is there. And I realized I tried for him, and it was impossible. So if you go to the mushroom page, it's perfectly informative. You can read it, you can enjoy it, but it doesn't take you to where you want to go, which is the ability to classify mushrooms. And in fact, a few years ago when I looked, the Wikipedia page on mushrooms said, well, get yourself a field guide if you're trying to classify a mushroom. Okay, and so we think of the internet as something that is perfect. We can find all the information we need, but in fact, the information is maybe not easily accessible when it's starting with a picture. And the info is there. So there is this Amanita pantherina. That's the mushroom he's looking at. And if you read the page, at least as it was written 2 or 3 years ago, it was very funny because it says it's a terribly poisonous mushroom, don't eat it. And then you go down the page, and it says it's considered to be a delicacy in China. And so I was left with wondering what's the poison all about. Anyway, so this is just to get going with the idea that in the world we face questions, and so we might say, what is this? And so, if I ask Terry would say, well, it's a bird, right? But that's not. And this is what your typical deep network would say. It's a bird. That's how it was trained on ImageNet. But that's not what I want to know. I know that's the bird. I want to know what species is it. Is it typical of San Diego, or is it a fluke that I see it here? Or here, oops, sorry. Let me go with this. It's faster. Okay. And here I may go to the dermatologist to ask, is this dangerous? Or should I take it out? And the dermatologist says, well, I don't know. Yeah, no, it looks all right, but come back next year, I'll take another look, and so on. But this process takes many days. I have to make an appointment. I have to remember it. I have to drive there. I have to waste half a day to be there. I have to pay $100 for an opinion on something that wasn't most likely relevant. So wouldn't it be nice if you could just point your iPhone or your smartphone, and it would tell you what it is, and so on. So you go around Rome and you find this, who is this guy? And it turns out it's Emperor Nero, somebody quite famous, but you wouldn't know otherwise. Or you may ask, what is written here? In what script is it written? When was it written? And so there are many questions that we become numb to simply because we don't have any hope of solving them. And yet, if the expert was there next to us in that moment, we'd just point at the thing and we say, what's that? And the expert would tell us a wealth of information. And we have the confidence that, in fact, information is somewhere in the web, and we simply cannot dig it up. And so here came the inspiration for the project that we call Visipedia. And it's done in collaboration with Serge Belongi, who used to be a faculty here. Many of you remember him. He's a wonderful person. He's now at Cornell Tech. The idea is very Napoleonic, is to say, well, there are experts about all sorts of visual things in the world, from motorcycle carburetors to flowers to birds to brain cancer to anything. And wouldn't it be nice if we could harvest all of this wealth of knowledge, bring it all in one spot, which is basically the cloud, and through the cloud to your smart device, and therefore give anyone, anywhere, at any time, access to this information immediately? Wouldn't it be nice if we could do that? And it feels like computer vision is getting there. What is blocking us from doing it? So here is a graphical representation. So we have people with visual questions on the left, on the right, and it would be nice to build in some way a bridge between the questions and the information. And so the question is, how do we get this done? What are the problems that come up? And if you work in computer vision, your knee-jerk reaction is, oh, okay, since 2012, we know that deep networks actually can do a lot for classification, so let's just collect data, let's train deep networks, and we're done. What's the big deal? Just wait, and it will be good enough. And so my talk would end here if that was the answer, but there are many interesting questions that come up in this pursuit. It truly, it gets to the bottom of what does it mean to be a scientist, and how do we go around the world. We use our senses to look at things, and then we organize them, we discover patterns, we file them away, we taxonomize them, we develop systems of knowledge. And how do we share information with our fellow humans? How do we know if something is true or false? And so it's very fundamental questions. And so I want to go through just a few of the challenges. It's not all of them, but we've worked on this for long enough that there are probably 2 or 3 talks worth of material. So I'll cover a few. So the first one, I want to start soft. And so is fine-grained classification. So one thing we realized right away, so having to pick some subfield to work on in order to make up our mind, we decided to work on birds initially. And the reason is simple. So what we thought is so first of all, there is a wealth of bird diversity. There are about 10,000 species in the world. People who like birds buy expensive cameras to take beautiful pictures. By now, they're all digital. And so these people must be computer savvy. They must be filing away their images, and they must have websites where they share images. So there must be a community online that is ready to go for us. And so we came in touch with the Cornell Lab of Ornithology, which is the premier ornithology lab in the world. And indeed, they had just set up a website 2 years before, which was collecting checklists from birders. And so they were collecting all the information from all the birds in the world, what do they see, what they don't see, to map out populations. And they were discussing in that moment how would they possibly upload, let people upload also photographs. And so we came just at the right time to work with them. And so, of course, you want to train a classifier. And again, if the classifier job is to say bird, you're out of luck. This is not interesting at all. So you want it at least to say that this is a sparrow. And actually, as you will see in a moment, there are lots of different sparrows. So it's actually a chipping sparrow. Okay? So this is the level at which you want to go. And you want to go to this level in many different domains. And so here, just for your edification, this is the picture from a book on sparrows. And so these are a bunch of sparrows that are out there in the world. And you realize that it's indeed fine-grained classification. So the worst case, or the most interesting one, is chickadees. And so people, if you go on websites of birders, people debate to no end whether they just saw a Carolina chickadee or a black-capped chickadee. And I leave it to you to figure out so there is a little detail on the shoulder that is different, but people are venomous with each other if they get the classification wrong. So this might be a big problem because deep nets were developed so over the years on MNIST and so on, and then they were tested on ImageNet. That was a big revelation. But ImageNet is collected without an attempt to taxonomize at a fine-grained level the world. It's sort of Barracuda versus Abacus versus Buddha and so on, right? And so it's very broad, distinct categories. So the question is, will deep networks manage to deal with fine-grained categorization? And if not, what needs to be done? The second challenge is, as I told you, there is a great number of categories. This is the taxonomy of birds. And so there are about 10,000 bird species. And so, how many objects in general do you want to recognize? And so the estimate, and so these estimates vary a lot, but the estimate would be about 10 million species of plants and animals, give or take. Now, the people I work with at iNaturalist, which I'll talk about in a moment, tell me, well, if we got to 1 million, that would be all that people will ever see, because there are so many that you never see because they're rare or small or whatever. And then you have how many man-made objects are there. So if you look at the number of parts of a Boeing 747, it's tens of thousands, hundreds of thousands. And then you have all sorts of bottles for drugs you find in a drugstore. You have, again, carburetors of motorcycles and so on. So it's many millions. And how many landscapes can you recognize? How many remarkable mountains do you have in the world? And so on. So you can go. So it turns out celebrity is another interesting one. So I was thinking, well, celebrity is not a big problem because by definition, to be a celebrity, you must be one of 100 people. But no, now I know because I'm at Amazon spending some sabbatical time there, and I have a celebrity detector. And so celebrities are about 500,000 people. So you wonder, how can you be a celebrity if you're one of 500,000? But that's the number. How many Chinese characters were tens of thousands, and so on. So you have probably, so the goal might be between 1 million and 100 million things that you want to recognize. That may be a thing. So again, do deep networks scale well to many things, or do they show signs of fatigue when you load them with too many things? So these are very technical questions that you can resolve in an experiment, and I'll go there in a moment. Another one is the challenge of the long tails. And so what's the challenge of the long tails? Well, this is when we started collecting birds. We did this plot at the beginning when we had only 700,000 specimens here, 750,000. And if you group them by species and you sort a species by numerosity, here is what you see. So this is a log scale of the species ID. And so here we go to about 10 to the 4, which is where we expected it to be. And so these are images uploaded by birders around the world. But what is interesting is that the count, the number of elements or specimens, varies a lot from almost 10 to the 4 all the way down to basically 1. Okay? And if you see that after 100, so at 100 species, so only the first 100 species in this sample have 1,000 specimens, and only 1,000 have 100 specimens, and beyond that you have the vast majority, so it's 90%, that have below 100 specimens. And there is no way to fix this. The world is again, a long-tail distribution. So if you talk to doctors, eye doctors, and you ask them, how many pathologies do you see in the retina? Well, there are about 600. How many do you see day by day? Oh, day by day we see about 10 or 15. And then, throughout my lifetime, I might be able to see 100. And then there are many more that are seen very rarely by doctors around the world. So the number of training samples is very variable. And you cannot fix that. You cannot fix that. And so when ImageNet was collected, and later we collected another data set called COCO to increase the number of training examples, we went to incredible lengths to have a uniform number of training examples. And we thought we were doing something good for the computer vision community because they need lots of training examples to test their algorithms. And then we realized we were creating this artificial world in which people are lulled into the presumption that they will find a uniform distribution of samples. And truly, the interesting question is, what do you do with 90% of your data for which we have very few samples? And so the question is, how do you train with very few samples? And I get to that point in a moment. Just if you were curious, what are these birds? And so here you have the bald eagle, the most photographed bird, at least on as seen by the Cornell Lab of Ornithology. And then you have a pigeon, and here is a prairie lark, just in case you want to know. Now, the fact is that for our machines, we know, and you will see it in a moment, we need to have hundreds of training examples, so around here. Now, if you ask a birder, how many training examples do you need for becoming good at your task? And they tell you, well, give me 3 or 4, give me 5 or 6, they say. And so this is the human threshold for learning a new species. And you see that humans can go out to very many species with what is available. And there is this huge gap of about a factor of an order, 2 or 3 orders of magnitude between what is needed by humans and what is needed by machines to get good at a task. Now, I will not be showing those results, but as of 2017-18, we have a number of examples of deep networks that achieve or surpass the ability of human experts. And so one is the one we put out for iNaturalist, and another one we put out for Merlin Bird ID, which recognize far more species than any human can fit in their head, and with great accuracy. And then there are papers on dermatology, and then there are papers on AlphaGo or whatever. So that you have many applications where the machine is getting better than a human. But when you look at how many training examples the machine required, it's usually between 10 and 100 lifetimes of a person. Okay, so the efficiency of training is not as good as human. And since here we are amongst neural computation people, we know that humans are not magical. If a human can do it, well, I'm an engineer, I want to do it as well or better, right? So that's my challenge. And so that's something to work on. And so just to show you that this repeats, these are trees in Los Angeles, which is another project we work on for mapping all the street trees of Los Angeles and recognize their species. And again, you see this same zip flaw distribution with the long tail. So here is an experiment that my student Grant Van Horn carried out last year, in fact in 2017. So don't worry about the dotted lines, which these are SVMs. It was sort of a control experiment. Focus on the solid lines here. And so we can draw a couple of lessons from this experiment. So here is what happened. He took the bird data set, And as you have seen, for some species, we have an enormous number of training examples. And so he trained using a variable number of training examples, a deep network for classification, and he watched how did the error decrease as he trained with more items. By the way, if you deal with deep networks and if you train deep networks, you should always produce a plot like this to see what goes on as you increase the number of training examples. Error, and so the right way to plot the data, people typically use the correct rate or the accuracy. And it's a wrong way to look at it because the accuracy, really you want to minimize the error. And if you can halve the error, that's the type of gain you want. And you see it in this log plot of the error. So here is 1%, 10%, 100%, right? So here is the first observation is that you can drive the error down to very small percentages. So it is about 3%. And the images that come through these borders are quite terrifying. They're a bit pixelated, they're difficult. So it's great that these things work really well when you have enough, which means 10 to the 4th training examples. And the sad news is, as you decrease the number of training examples, you increase the error by a factor of 2.5 or 3 each time you decrease the number of training examples by a factor of 10. Okay? So this is a back of the envelope. I've seen it over and over again, so just remember it. It's not a law of the universe, but it's the current state of the art and technology. So that's the first thing you should remember. So these networks are very hungry for data, and a human would be more or less, if you will, here, and the machine is here. Second one is you see that the solid lines are all on top of each other, and the solid lines were obtained. The blue one is only 10 classes, and then 100 classes and 1,000 classes, red and green. And you see that on top of each other, which means as you increase the number of birds, the networks can eat them up. It's no problem at all. So the question of fine-grained categorization and the question of how many species can you deal with, right now it doesn't look like we're hitting any ceiling. And of course, there is no guarantee that going forward it will keep being that way, but it looks promising. And so we have data for iNaturalist, which has 50,000 species in it, and it still looks the same way. Okay, so and so there is a big problem with the tails, but not with fine-grained or the number of species. So here is another example. In this case, these are camera-trapped data from Sarabiri in my lab. And again, we have camera-trapped data coming from the whole of Southern California, Nevada, and Arizona, lots of images. And you see the same behavior. Now, this is across species. It's not just increasing or decreasing the number of training examples. But you see here badgers. We only have 5 training examples. They're quite rare here in the Southwest. And so the error rate is 70%. And if you go down the curve, you see opossums, where we have thousands of training examples, and the error rate is down to 2% in classifying the animals. Okay, so the same behavior, and this line has more or less the same slope. Now, why do we need so many training examples? And this goes to the core of one of the problems with deep networks, and it has to do with the fact that we have to deal, or the networks have to deal with a great variability in the stimuli, and so you want to have all the possible variabilities in the training set. And in order to have that variability, you've got to have an enormous number of data. Otherwise, the network will miss some corner cases and will not be able to deal with them. And the sad part is, so these are chickadees, and they seem to be able to hang upside down. But if I saw a penguin hanging upside down from a tree, I wouldn't be confused. I would just say, what does a penguin do upside down on a tree? Somebody must have been hanging it there or something. And so it's clear that humans can generalize from one species of bird to another, for example, the pose or the environment in which you find the bird and so on. And these networks can simply not do that. And so the question is, how can we help these networks generalize? And you will not hear an answer from me today about that. But one approach may be going back to Rob Fergus's thesis, which was pre-deep networks. Here, Rob Fergus was training without supervision, so without sort of clicking on the data. his algorithm, which was a Bayesian algorithm, was able to identify common structure across, for example, these motorcycles automatically. So the algorithm only knew that somewhere in the picture there would be a motorcycle, and it was able to discover, for example, the front wheel as a pattern, or the saddle, etc. And so I think that we need to go back to this kind of work with our deep networks and identify parts from the birds that we have lots of examples for, and then move on to the birds that have fewer examples. So something like this. But there are other thoughts in the community. For example, some people think, well, you don't need to explicitly identify parts. The networks will do it. It's just a matter of getting the right loss function in place, and then the networks will figure it out. And so this is a little bit of a debate going on. It's not that I'm not religious either way, but it's a fun thing to think about. And if you're a graduate student thinking about these questions, this is a perfectly good one for your PhD. So to summarize the first part, we worried about fine-grained categorization, but it was a piece of cake. The networks can absorb it. Up to now, we don't know. We don't have theory to tell us that it will keep going, but number of categories, another piece of cake. And we saw that the true difficulty is with the long-tail distribution, and we don't have answers to that. And so, again, if you're thinking about a good topic for your PhD, this is a very good one.
What kind of cake are those?
That's a good question. So I would say that one, yeah. So this would this be a Zuckertarte? No, because maybe a tiramisu on top. Yeah. They're all, let's say that they're caloric bombs. I wouldn't eat them every day. Okay, so now we get into things that are a little bit more strange from our common day-to-day activities. And it's a one of dealing with experts. So the information is in the head of people often. And so it would be nice if one day the machine can also discover new categories by itself. And I'll talk about that just a little bit at the end. Really, the information we want to harvest now is from experts. And so there are some experts in art, in pathology, botany, and so on. And so the question is, how do we get it? And so this is a typical question that is not asked in a machine learning talk, where the assumption is, well, somebody just did the work and they prepared the data set for me. Thank you very much. Let me take it. And people compile this information in ways that are more digestible. So this is a flyer that is put out by the Louisiana Department of Forestry or whatever to identify the ivory-billed woodpecker, which is believed to be extinct, but there might still some specimens around, and some people report it from time to time, and the forestry people are sick and tired of hearing these reports because it's always a duck or it's another woodpecker or whatever, so they put out this information. So the information is there in some forms, and so how do we get it? And so we hit this question when we collected our first bird data set. And this is the worst example that happened to us. We got a list of birds from Wikipedia. So we're not systematic at all. This was pre-working with the lab of ornithology. And we got names from Wikipedia. And we scraped the web for pictures of birds. And here there are two different species that are not even related. Well, they're both birds, but not very related. And one is called indigo bunting, and one is called blue grosbeak. And you see that they're difficult to tell apart. Well, a birder would tell them apart in a moment, but for you in this moment, it's not easy at all. And of course, the people who upload the pictures to the web are not skilled necessarily, and so there were lots of errors. And then there were other pictures that were unrelated of a canvas bag with one of these birds on that said indigo bunting, but it was not the bird we're looking for. So we had to have Amazon Turkers sort the pictures and clean up the collection for us at some point. And we realized that we were making many mistakes, and so we thought, okay, how do we deal with that? And we realized that when we looked at the two types of errors that people make, so we had some experts, annotate this particular collection, and then we looked for the indigo bunting pictures. And so each dot here is a mechanical Turker that has gone through a bunch of pictures. And here is the rate of correct rejection, and here is their hit rate. So here is how often do they say, yes, it's an indigo bunting, where it is indeed an indigo bunting, and here is how often do they say, no, it's not an indigo bunting, when indeed it's not an indigo bunting. And as you can see, the annotators have completely different behaviors. And so when we looked at this, we realized that we couldn't go with majority voting because you're just comparing apples with pear. When you do majority voting and people have these completely different ways of responding to the stimulus, you're just averaging noise, and before you average it out, it's too bad. So we wanted to know a little bit better what they do. And just to give you some guidelines, so this is the ROC curve. It's flipped with respect to what you're used to. And you see that there are some people here that have exactly the same error rate, and they're just differing in terms of the threshold they use for deciding a yes or a no, right? And so, so my student, Peter Vellinder, liked to put these cartoons. And so, so these are the best annotators, the ones who make no errors are up here to the top. And these are going completely at random. They're just responding at random, yes or no. These are optimists. They always say yes, it's an indigo bunting, and so they get fantastic hit rate, but very bad correct rejections, and pessimists always say no. Okay. So, and these are adversarial, they respond, they're anti-correlated to what they should be doing. Right? And so I told my students, oh, these are students at Stanford who are trying to mess up your data collection. And so that made it very interesting for my students. So we thought, okay, so how can the machine deal with all of these different opinions? The machine clearly wants to know who is good and who is bad, and who has a bias towards saying no and who has a bias towards saying yes. And even if you have an adversary that is completely anti-correlated, they give you perfect information. You just have to flip a bit, right? And so the machine shouldn't be averaging votes. It should be understanding things. And is there a way to estimate these parameters online? And so here is what we did. And so here comes in, if you will, the psychophysics part of the story. This is the model we built. So Zi is a binary variable. Is there an indigo bunting or not in the picture? I is the index of a picture. And once you know if there is an indigo bunting and you know which viewpoint you took, which specimen it was, etc., you can construct the image. So the image is a function of all of these parameters that we don't care about and a binary variable up here. Now let's suppose that the best birder in the world, the Einstein of birders, came along and you ask them, is this an indigo bunting? And then what would they do? They would ignore the branches and so on. They reorient themselves toward the bird, and they extract a few parameters from the bird, which are maybe the color of the plumage, the length of the beak, the color of the eye, and so on. So think about 10 parameters, something like that. So these are 10 golden parameters from image I that ideally will help you classify whether the bird is an indigo bunting. And then a real annotator or expert is expert J, has in their head a corrupted version of the perfect measurements, corrupted by some noise. And so the idea is that there is some underlying, so here is a one-dimensional xi, some underlying distribution for xi when an indigo bunting is there. So you have your usual Bayesian point of view of suppose that there is an indigo bunting, what does xi look like? And then depending on the picture, so this is a perfect indigo bunting, so you will have a high score, you will be on this side where there is no other competing image. And if you have a problematic one, it might be more towards the center, it's in a more iffy position. And then if you have a canvas bag, well, this is clearly very low on the score. And then depending on who is looking at the pictures, they have, starting from this real underlying xi, they have a yi that has a certain distribution of noise, where somebody who really doesn't know what they're doing, they have infinite noise, and so it's all a blur. So it turns out that if you have this model in mind, the way you can think of it is, here is your Zi, here is your binary variable, here is your perfect measurements, here is what is in the head of annotator J, and the annotator will produce a label based on some classifier and some bias they have in their head. And down here you have which index I was assigned to which annotator J. And so it turns out that thanks to the work of people who in the 90s, we have expectation maximization, we have methods for estimating hidden variables. So we want to get at Zi, there are these hidden variables here that characterize the annotators. And the only thing we can observe is the labels that were assigned to a picture. It turns out if you have enough data, you can back out these parameters, and by backing them out and having modeled them explicitly, you can also back out what is in the head of, so what is the reality out there. And so you get a bonus, which is you estimate what people think and what is their school of thought in classifying these birds. I hope that this is clear. And so for us, this was a breakthrough moment because we realized that spending time thinking about the psychophysics of the problem was giving us some mileage in understanding how people think and how people respond to stimuli. And so this was giving our machine, which is sitting there and it has to deal with lots of experts, a means of cross-referencing what the experts are saying and deciding who really knows what they're saying and who instead is a fake expert and doesn't know it. And so if you will, the tables are turned in a typical machine learning situation. The expert is an oracle. You don't question it. It's golden. And then the key problem is training your system. And so the question is, will the expert trust the system? And here it's the opposite. It's a machine is sitting there. It's interacting with lots of people across the web. And it doesn't know if these people are legit or not. And so it's the machine who has to build confidence in the people and decide if it wants to trust them. And the machine owns the truth. And the people only see little specks of the truth or only know little specks of the truth. The machine is integrating the information from all of them. Now, so this was done in 2010. And if you read our latest papers, we have integrated computer vision systems with that machinery I showed you before. And so here I just show you a flow diagram. I'm skipping over all the variables and details. But basically, once you have a computer vision system that is being trained from the data set, from the annotations it gets, and so the machine in its belly has a developing understanding of what's going on out there, and it's making up its mind as to how to deal with the data. And here you have the crowdsourcing. So here I have Amazon Mechanical Turk, but it could be naturalists out there in the world or pathologists. And you have human annotations. And the system keeps learning, and it keeps sending to the annotators the most interesting or difficult cases. So it's a sort of active learning. And it's developing a model of how each person that it's interacting with is working. Okay? So this is the bigger picture point of view. And just to give you a sense for how we operate, so here again is a set of experiments that were conducted with two populations, mechanical Turkers, they are the mastered ones, and sea Turkers, these are the citizen scientists, if you will. And so these were birders that we recruited. And of course, the birders are far fewer than the mechanical Turkers. They respond less fast. They are less willing to annotate. And so we have few annotations for them. But the machine can estimate the parameters in the heads of the annotators. In this case, the estimate is what is the probability that the annotator or the expert gives you a correct annotation. And here you can see that the citizen scientists, the birders, are estimated to have an 80 to 100% probability of being correct, and the mechanical Turkers are much lower. And so we have a data set that is annotated for ground truth, and so it allows us to compare the predicted, so what the machine is estimating and what really we are observing. And so you see that the two populations are separate, and it turns out that since there are many more of these Turkers, it's still worth sending out the data to them. It's just that you have to take into account that they have higher error rate, and so you need to have more opinions to get to the truth. Okay, so let's get to a couple of fun apps. So here are two apps you can download to your phone, Merlin Bird ID. This is specialized on birds. And the goal of this one is to be basically always right. And so the error rates are extremely low. The training set is huge. It's incredibly well annotated. It's wonderful. But it's all managed by people who verify that the training data is good and all of that. And here you have iNaturalist. So this is in collaboration with the Cornell Lab of Ornithology. And here you have iNaturalist, which is in collaboration with the California Academy of Science. And iNaturalist has the opposite point of view. It says, let's 1,000 flowers bloom. Let's put this app on the phone of millions of people. People will go on walks. They will want to know what's that flower. They will photograph it. They will post a picture, whether they know or not. They will post a picture. Somebody else will come in and will express their opinion on what's going on. And the machine will watch all of this noisy interaction and will slowly learn how to classify the species. So let me show you first. So you will download it and you will. So now Merlin, Bird ID. So here is the first version of the app. It could classify 500 species, and now it's 3,200. So if you download it. So it basically covers the northern hemisphere quite well, and a little bit of Central America, not much of the southern hemisphere. And it's all happening as we speak, so we get about 100,000 new images of birds every week, and the Cornell Lab of Ornithology uses software that my student Grant Van Horn wrote to retrain the system every now and then and add more species. And so the way it works, you see a bird, and you have some interface that allows you to single out one bird with this frame, and then the system will tell you, oh, it's a hooded merganser, okay? Now, this is an experiment that my friend Deborah Mooring did. And so she said, your app works really, really well. Look, it classified this bird. And she sent me this picture. I thought she was joking. You know, what is the bird? And it turns out that the bird is there here. And it gets classified as an oriole. And Deborah told me that she had binoculars. She assured me that she had identified it herself. And it was correct. So this is to tell you that it's, so that, you know, this is thanks to deep networks. It's not thanks to work we did, but it's to tell you that you can achieve very good accuracy, you know, beyond what a typical human could possibly achieve. And this is from a naturalist. Here you have the distribution of observations around the world. You see that they are mostly in North America and Europe, with some hotspots in Australia, New Zealand, and Japan. And it's hundreds of thousands of people, so maybe you have to see it here. So this is you see that the number of users since we put out the computer vision system is going up a lot. And this is a log scale version where you see that it's reaching, in fact, 500,000. And the number of observations, species, and so on is going up. We're about 10 to the 5th or so. And the machine can recognize 20, 30,000. So this is a walk I took on the beach a few months ago. And so these are things I photographed, and you can feed them into iNaturalist, the app, and it can recognize them for you. And so I'm happy if you download it now. I'm happy after the talk to help you get going. So you can feed a feather. Here is a fly that was on my plate one day, and so I identified it. And so, but here is the strength of the system. So in the system, again, there are hundreds of thousands of people. And so you have to think that we have a giant confusion matrix of 20,000 or 30,000 by 30,000, namely for each person. So each person, we know using some Bayesian algorithm, how likely are they to make a mistake when they classify a butterfly or a lizard or a fox or whatever. And using this, the machine can decide when enough people have expressed an opinion to have certainty about the outcome. And it also has a computer vision system built in. And so the network, this system also has its own judgment that it's adding to the rest of the mix. And so here is a picture that somebody sent me from Arizona. And using the system, so I decided that it was a banded sphinx moth, and I felt pretty smug about it. And then a few people came in, and they all disagreed. They thought that it was a white-lined sphinx moth. And so you see that these are the names of these people. It's not clear what their names are, but within a couple of days, and I have no idea what pushes people to look at other people's observations, but that's what happens. And so in the end, the system decided that, okay, this is a white-lined sphinx moth. It's not what this idiot Perona was thinking. And it's because, again, the system knows how to, yes? Okay, so I think I think that this is the date when I uploaded the observation, each observation. So there is a whole database behind the system that is quite interesting. And you may think of them as biology. So it's like a lab book in biology. Everything is labeled as an observation by a person on a certain date. And then there are annotations. They manage an amazing complexity. And we surf on top of their data. OK, so, sorry? It was not an April 1 joke. Anyway, I have lots of examples like these that are quite interesting, and you will play around with it yourself. So this, I claim, is the first, if you will, the first machine learning system that is out there in the wild, sitting there and interacting with a very large crowd of humans on data that are fairly complex and learning in the process. Sort of is almost an autonomous system that is there. Learning and becoming better by interacting with humans in the right way. So something that is missing from this is the ability to identify an expert that should be able to break a tie. So the system is only waiting for people, it's passive, waiting for people to come in and express an opinion. It's not polling, and that's something that I want them to put in soon. Okay, last challenge I want to talk about is the one of discovery. And so first let me make a general philosophical point. So where are we now? And so people, if you read the newspaper titles, everybody talks about AI, the AI revolution, AI companies, and so on. And I put here a giant question mark for reasons that will be clear in a moment. And so we've got here through three paths that have collided with each other at some point in time. So from neuroscience, we got the idea of deep networks, Fukushima, Yann LeCun, in the late 80s. And at some point, it became possible to use them on very large annotated data sets because the web made lots of data available, and Amazon came out with Amazon Mechanical Turk that allowed us to annotate the data sets. And this was the work that came out of my lab and then many other labs also in the early 2000s. And then, of course, Moore's law that gave us GPUs on which we can train these deep networks. So these are the three drivers of progress. Now, do we have AI? And so in my mind, there are three levels at which a machine can understand the world, or a human or a butterfly can understand the world. So one is memorization, recall. You get some data, and then you can quickly look through them. And so if you think of relational databases, that's what they do. So there's a solved problem, no problem at all. Prediction and generalization is something that we feel our deep networks are doing right now. And I will disabuse you of this notion very soon, that it's not as good as we think. And understanding mechanisms and understanding how to intervene in the world is a third level in which we understand cause and effect. And this is not there at all. And I'll show you some fledgling efforts in the direction just in a moment. So just to make the point clear of this, that the second level is not yet reached. So this is a test I ran on Clarify, which is a cloud-based system that can associate labels to images, and it's the product of Matt Seiler, who is a student of Rob Fergus, whom I mentioned earlier. This company is out of New York. You can feed, they have a nice demo online, you can feed images and get labels. And you can see that here, it just nailed the cows in each one of these pictures. It's pretty clear that the network knows that there is a cow in the picture. And I don't think it distinguishes between cows and bulls. So cow means bovine or something. But you can go nuts with the type of images you put in, and it's very good. So you say, wow, we've got it. The machine knows cows. But since I know how it works, I can make it fail miserably. So how did I do this? How did I make it fail? And Nuno.
Placing the cows where they should be?
Exactly. So I looked for pictures of cows in unusual environments. And as you can see, the machine has no clue at this point, right? So what's happening here is the people who train the machines get the images the same place where you get them, namely they scrape the web. And on the web, you have lots of pictures of cows in verdant Wisconsin or Swiss pastures. And we don't have many pictures of cows on the beach. Okay, there's just very few. And so the machine is utterly confused here, and it gets some signal that is sort of conflicting. And so it doesn't, in most of these pictures, it doesn't even see an animal, right? Or maybe, I don't see any animal notion here. So this is very, very disappointing, right? Very disappointing. So if you think of it from the point of view of prediction and you want to drive your error rates low, this may be a good approach if you assume that your final user will have the same statistics of images as the ones that were used for training, because by definition these pictures are very rare. And so you say, okay, yeah, I will fail with cows on the beach. I can live with that because cows are never on the beach and nobody will ever wonder what is that thing on the beach and so on. But from the point of view of our science of computer vision, this is a very big disappointment. No human would ever be confused in this way, right? So this tells you something that AI, well, I don't see much of the eye. The intelligence is not there. So what we have is just massive pattern matching machines, okay? And here, this is very repeatable. You can do it with ducks and so on. It's not a fluke. Okay, so so clearly, even the second level is a little bit in question. The machines are not really able to generalize, to learn a pattern and generalize a pattern and associate. Now, the other point I want to make is the question of causation. So if I ask you, what do you think about this man? What's happening to this man? You say, well, it's clearly he's sick. And I say, Angela, why do you say that he's sick? And I don't know, Angela, if you want to respond or not. Yeah, he's in a hospital, there are the doctors, he's in bed, he's clearly sick. And I say, okay, you say that he's sick because you see the doctors in bed. And Angela says, yeah, that's exactly, why do you ask me? It's exactly why you say it. And I say, okay, well, so what the machine should understand is that he's sick because of the doctors in their bed. So he should get better if he gets out of bed and he sends the doctors away, right? If that's the cause. And clearly this is not the cause. So we have a problem with causation. So we do very well with correlation. And correlation is excellent for prediction, but not for intervention, as I will point to you in a moment. So if you think of probabilities, I want to give you, if you haven't thought about causation in a while, here is how it goes. So if you think of probabilities, you can think of the variable x is in bed and variable y is fever. And when you draw an arrow, it just means in your Bayesian mind, it just means that you're studying the conditional of him having a fever conditioned on x being in bed or not in bed. And this is perfectly fine thing to do. So you say, well, the probability of him having a fever if x is 0, he's not in bed, is 3%. And it's maybe 90+% if he's in bed. But truly the causation goes the other way. It's the fever that causes him to be in bed, right? Now, you can also draw your Bayesian arrows the other way around. There is no problem about it. And so what the probability of him being in bed if he has a fever? And you can study those probabilities. There is no problem at all. So in your Bayesian world, you can go both ways. You just look at correlations. But the Bayesian world doesn't tell you about causation. Okay, so here we're following the definition of Judea Pearl. And so he has this other notation. So you can think of in probabilities, you can think of x being orthogonal to y if p of y given x is not p of y. But in the case of causation, it's a little bit different. So I'm using arrows that are shaped differently here. So you have this do operation in place. And so if p of y, when you manipulate x and you fix everything else in the world, is not equal to the probability distribution of y, then there is a causation of x towards y. And so the way that Judea Pearl talks about it is if you're interested in the fever and in bed, which one is the cause of the other, you've got to isolate all the other possible influences, and you just tighten them down. You just you block them. And now you want to intervene. And for example, you can give the person an antipyretic and decrease his fever and see if he remains in bed or not. And most likely the person will get up as soon as there's no fever. And otherwise you can tell him, get out of bed and see if the fever goes away. And now you know which way the cause and effect are. So you have to be able to operate on the world. So as we go in our with our AI, supposed AI, as we go from static sets of images where the only thing we want to do is correlation. So if you go and work for Google, your job is to increase the amount of advertising that Google can sell. And the way they can sell it is interpret the images that are in somebody's email so that you know what is in there, so that you can advertise that thing. And you see that picture before, you can deduce from the fact that he's in bed that he has a fever, so you can advertise antipyretics, right? But because people with a fever, but you don't know the cause and effect. You just did it by association, right? So truly, if you want to take care of the person, you've got to know what causes what. And our machines are, from just observing the world, cannot do it. And as we build robots like the autonomous driving cars, they will need, since they are interacting with the world, they need to know how to make the world different. If they see something, they have to act on the world to change it, and so they don't need to learn that. And so just 2 or 3 more slides to go to the point. So here is a baby experiment, just to give you an example of what you can do. Suppose that you train, you use your MNIST data set to train a classifier. Well, it's nature somehow decided on the images that are there in the data set, decided on the x's associated to those y's. And so your classifier only saw a certain thin slice of all the possible ways in which you could write numbers. And so it doesn't know what kind of images causes a human to say 6. It just knows which set of images within MNIST. And so if you want to teach the machine to know what a 6 is really, what causes a human to say 6, you've got to go to the lab and manipulate the x's and y's and do a study like the one we saw before. And so how could you possibly, so you want to do it automatically, how do you possibly do it? And so here is an idea that my student Krzysztof Haupka explored a couple of years ago. As you've trained the classifier, you now know how the weights are determining the transition from the images to the classes. And so you could possibly manipulate, you could ask the classifier, well, give me, start from an image of a 0 and give me a minimal manipulation that will produce a 6 from the 0. And then you know if the system knows what a 6 means, because it has to produce a 6 that is out of sample with respect to all the 6s it has seen before. It has to manipulate a 0 into a 6. So this is just purely one way you could do it. And so this is what we did. So if you, so first of all, how does the experiment go? So you have to have a way to have the world respond to what you're doing. And so that the machine would produce these funky images, and we would post them on Mechanical Turk, and people would type in what they saw, right? So that we would know. So the system was able to carry out a controlled experiment on the human brain to see what kind of images cause a human to say 6 or 5 and so on. And so the challenge for the system was to start off from valid MNIST images and produce an image that was minimally changed, minimally manipulated, and that would be assigned this class by a human. And so a system that does 0.5% error rate on MNIST, I mean, you say it has nailed MNIST, it knows what a handwritten digit is. Well, if you study it, we will see that it will produce images such as these. So this is a 6, and it wants to produce a 2. Well, it will add 2 or 3 pixels here or there. And so it pushes the buttons of the network in ways that are completely unseen before. So this is like adversarial example. Some of you know that literature. And it convinces the network that this is a perfectly good 2 or 3. 3. So the network is convinced with 100% probability this is a very good 3. And you see that this image is completely outside the envelope of MNIST. And so that's why you can convince the network about anything. But if the network is allowed to carry out experiments and it sends out these baby steps to human annotators, and the humans say, well, look, this is still a 6 for me, or this is still a 5 for me, the network very quickly, by experiment, can learn what is the causal relationship between an image and the human saying 1 or whatever. And so these are the manipulations, and you see that there's a 7 morphing into a 2, and by this time humans will say 2, or a 6 morphing into a 3, etc., etc., etc. Okay, so these are baby steps in creating an artificial system that can study causation. But still, I think that we are, green for trivial relational database stuff, and generalization prediction we're yellow, and for intervention and understanding causation mechanisms we are at 0. So since we are late, let me skip these little slides because I've told you about this. These are my collaborators. I think one is missing, but anyway, so Serge Belangi, you remember, and these are lots of very talented people. And there are many papers about the things they talked about, and you're welcome to ask me questions afterwards. I'll help you, I'll direct you to the right papers. Okay, thank you.
Okay, we have time for a few questions, and pass the microphone, please.
My question is about the lead-up work to iNaturalist, how the system figures out, basically out of this noise, figures out who's thinking what. The question is, does the system actually have some ground truth so that it can, is it running an experiment with the human annotators to figure out who's right and who's wrong, or is it like kind of...
Okay, so let's do a thought experiment. Let's suppose that there was one oracle out there in the crowd. As soon as the oracle chooses to give you his label or her label on an image, then the deed is done. Now, anybody else who has expressed an opinion, if they were in agreement with the oracle, then their probability of being correct is boosted. It's something we're trying to estimate. And if they were in disagreement, the probability of being correct goes down a touch, right? They made a mistake. Now, let's suppose that we do it for a while. Now, our estimate of the probability of people being right or wrong is now going towards high or low. And now, if 5 people that we consider trustworthy agree on something, or even if 4 agree, then we can safely assume that, okay, they are correct, right? And so now let's take away the oracle. And so we can take a Bayesian approach. We may start from a very watery or a probabilistic point of view on how well people will do. So we say, well, we think that people will be 75% correct on average. And so you can put also probability distribution on that. So everybody starts with these 75% brownie points. And so if you calculate how many people does it take, like suppose that 3 people agree and 1 disagrees. Is that enough to have 95% confidence in some label, yes or no? Well, maybe not. So you want to have maybe 10 people, maybe 7 of which agree and 3 disagree to have enough confidence. But now, once you've reached enough confidence on those hard-earned annotations, then you can start mirroring back those. So now we have a few items on which are fairly confident, and now we can start adjusting the probabilities of being correct or incorrect of the annotators. And the more we do that, the more we are sure about which people to trust, and the more their judgments will be valuable. And so it's a process that it's a gradient descent in some likelihood space, and it will converge somewhere.
Right. My question was about that first part. How do you get to that initial confidence from which you can go on?
Okay, so either so it's a usual Bayesian point of view. So either you start with a prior that you just pull out of thin air, and you say, well, I believe that people on average will be 70% correct, which is the best you can do. Or you have an oracle annotate a bunch of images, and you go out and you have them annotate, and you observe how often people are right or wrong, and you start off with it. The idea is that even if you start with, in quote, the wrong prior, which a prior is never wrong by definition, the system will converge to the right place as long as there are enough people interacting with the system. So.
Okay, next.
Do you use non-visual modality only, but another one, for example, for mushroom, odor or taste and whatever?
No, so we only work with still frames, which is a big limitation. But you have to start somewhere, and I know about computer vision. For me, it's easy to handle images, and when you give me sounds or whatever, I have to start reading up on how to deal with them. But the case of birds is one in which, all the birders tell us that they mostly work with their hearing, not with their sight. And so we should start handling sounds. So it's in the works. It's not there yet. And also video, how animals behave and so on is very interesting. And so that's another thing we want to do. And for taste or touch, we have no plans, but it will be fun.
Okay, Nuno.
So for the cow in the beach problem, do you think that we really need to be able to solve the causation versus correlation problem and to be able to systems that can do interventions and so forth, or is this the question of getting more data? And like maybe we can't do it right now. Maybe we can do it 20 years from now just by doing what we're doing now.
Right.
Where do you stand on that?
Yeah. So getting more data cannot hurt, right? As we saw, you can drive down error rates. Now, suppose that we were at 2% error rates, but that 2% was things that we care about. If you want to reduce, as you saw before, if you want to reduce the error by a factor of 2.5, you've got to collect 10 times more images. So all the sweat and blood and tears so far, well, you have to multiply it by 10. Now, for the birds, we have a certain stream of images, which is pretty abundant coming in. If we're not happy with what we have now and we want to double, so half the error rates, then we've got to collect maybe a factor of 8 of images. So it means that since we've been collecting images for 2 years now, we've got to collect images for 16 more years before we get there. So 16 years, I prefer to then ask my graduate students, instead of waiting for the images, well, let's try to think of something clever. And solve the problem anymore. And as a human that it's not because you saw cows on the beach before they can solve this problem. If a cow walked here, you would have no problem.
Well, but my ancestors might have.
Okay. But not in a seminar room, right? So we can build a very futuristic environment where we put a penguin and then... No, so I think it's... there is something we're not doing right. Of course we can brainstorm on what is it, but there is something we're not doing right, and it's probably not too complicated.
So Pietro,
yeah,
we have phobias, and we are attracted by attention to the figure. And when I'm looking at that cow, it's really the foveal representation that's being sent up to my object recognition system.
Right.
So one simple solution would just be to give your computer system a fovea, and use attention the same way we can do salience. I mean, that's already been done. It's effectively segmenting the object from the image and getting rid of the background.
No, you're absolutely right that that segmenting it out of the background is a great idea. And so maybe one way to think of it would be you segment it out. If the background is informative, it should help resolve ambiguities. People have pointed out that if the cow was very blurry and it was here, you wouldn't say that it's a cow, it was a sofa. But then here it's on a pasture, it's a cow. But if the image is very sharp and beautiful like this, so we've done that. So right now, the current system can, so there are systems that segment the objects, and we don't have enough data on how well they work. I feel that we see things a little bit better than that. It's not just segmenting. We know to associate the muzzle, with the horns, the hooves, and so on. I think that there is some structure that we learn that would help a lot and may not require segmentation at that point. Like segmentation is a bit of a heavy problem, but that's my guess. But you're right, that's a way to look at it.
One way to handle the background is by having that being recognized separately. So you recognize the object, you segment it somehow, and then recognize the background and use both for making the final decision.
That's right. And so you have a mixture of experts, one for the animal, one for the...
But, another question, yes.
So in that direction, the transform of the image that you give it, so you give you put the image into some feature space, I suppose.
Right.
And, but that feature space lives in a geometry space, right? Geometric space.
Right.
And so when you talk about segmenting an object from a background, you're talking about topology and geometry. So, so it may be that by adapting the feature space, you're essentially adapting. You could be more efficient to do that, but then you'd be actually going back into the world of geometry, and through the features which attach to that geometrical space. You see what I mean?
Right. Maybe. Thank you.
Okay, any other questions? If not, let's thank Pietro again.
Okay. Thank you.